This is my lab 5 for Physics 2211, last lab, Energy Conservation. I'm Divya Agrawal. Introduction. The purpose of this lab was to investigate the motion of a spring mass system with the mass oscillating back and forth. This is similar to lab 4 oscillations, but in this case my model is entirely computational and the mass is moving on a spring on a flat frictionless surface. The model will represent the energy principle of the total energy being equal to the kinetic energy and the spring potential energy. We will see that with my computations. The fundamental physics principles of this lab are Newton's second law of the net force being equal to the spring force. As the weight force is balanced by the normal force on the table, the net force is equal to only the spring force. Energy principle. Total system energy is equal to the sum of the spring potential energy and the kinetic energy. We will see that on the energy graphs for this lab. Useful formulas are the velocity update, position update, and for these I have an interesting way of doing it in my glow script. Kinetic energy and spring potential energy. Here is the first part of my glow script input. The mass initially I put to be 0.5 kilograms. The spring constant I set at 10 newtons per meter. The equilibrium position, meaning just the starting position, is 0, and the initial displacement I put at 0.2 just to give it some sort of starting point. Initial velocity is 0, of course, and the time step for the iteration is 0.01 seconds. The objects, this is just for the coding of the system, and the image, video, floor, and block and spring, standard stuff. The graph, I like the graph that I had this time. I feel like it's very nice looking. We won't be seeing the labels on my videos, but if you want to check out my code after, you'll be able to see that. And we can see that the initial conditions reflect that the velocity is 0, 0, 0, and the time is 0. Simulation loop. It's running for 10 seconds, and it's running at 100 iterations per second. So we can see the spring force calculation is what we've seen before. Acceleration, just the spring force, which is the net force over the mass. Standard calculation, there's no movement in the y and z directions. The velocity, I have an interesting way of calculating it. It's the acceleration times the time. If you think about this, meters over seconds squared times seconds is meters per second. The block position is equal to the velocity times time, because meters over seconds times seconds is meters. Updating the spring position is just the block position minus the spring position, standard length stuff. Kinetic energy 1/2 mv squared, potential energy 1/2 kx squared, and the total energy is the kinetic energy plus the potential energy. We will see that in our graph. We'll plot the energies on the graph, and then we'll update the time for our code. Here is my first simulation. We will see that as the block is oscillating left and right, the kinetic and potential energy are adding up to the total energy here, and it's creating a nice symmetric graph. That just means that the energy principle is satisfied because the kinetic energy and the spring potential energy is equal to the total energy of the system. What if the mass was bigger? Well, I set the mass to 50 kilograms in the simulation, and we can see that the total energy is still conserved. The mass is just moving a lot slower. And what this means is that for any mass in a closed system with this simulation, energy will be conserved, as no energy is lost to the surroundings and there are no outside forces. So the total energy will be equal to the net force times the total energy, not the net force. The total energy will be equal to the sum of the energies in the system, the kinetic and the potential. Thank you.